Hello everyone and welcome back to the tutorial video for week 11. I hope that you are all doing well. Before we get started, I once again would like to address some brief housekeeping. This week marks our second to last tutorial in this course. You have almost made it. What that means is that if there's anything you would like to see covered in tutorial form, now is the chance to ask. If there's anything that you would like to see covered in the tutorial for week 12, please send me an email by Friday, April 9th. If I do not hear from any of you, I will continue to make some choices about what we discuss. This week, we continued on our process of discussing hypothesis tests, and in particular, we saw a few ways that the likelihood ratio test could be used to make inference regarding parameters in multinomial models. This is an incredibly powerful technique, in part because multinomial models are an incredibly flexible class of models for representing observed data. I want to start today by talking about the particulars of the setup for these types of tests. Understanding the setup can help to simplify the problems we consider, since the tests covered in this section largely follow the same underlying techniques. It is only the particulars of what we assume that change. At its core, in this section, we will be making the assumption that we have data which are categorical. Sometimes, as we have seen throughout the course notes, these data will be continuous that we make into categories by constructing intervals. Other times the data have an innate categorical structure. In any event, our focus in this chapter is on answering the question, do these data differ from what we would expect, where we get to decide what it is that we expect. In particular, we think of the observed data for each of our categories as a set of observed counts, and then we compute a set of expected counts. Intuitively, the closer our observed counts are to the expected counts, the less evidence against our expectations we have observed. Speaking generally then, we have to make a couple of decisions. First, we need some sort of model that defines our expectations. This is going to be context dependent and in many ways follows the same types of principles we outlined in last week's tutorial video. The idea is that we specify some sort of null model that we use to determine how close to expectation our results were. Let's consider a few examples. Candies often come in bags with a variety of flavors. We may expect that a particular brand of candy produces an equal number of each of their flavors and randomly divides those into bags. This way, we would expect that each bag has an equal number of each flavor. This uniformity would represent our underlying null model. As an alternative example, a fast food restaurant is attempting to plan for their next quarter, and in the past they have assumed that the medium fries were twice as popular as smalls, with large occupying the rest of their sales. They want to test and see whether this trend has continued over the past year. This gives us a specific functional form to take as the null model. So one final example that's slightly different, let's think briefly about movies. In any given year, there is some fixed number of movies that will be released. Each of these movies could be classified based on its genre, and we could set up null models similar to those that we have already considered. Now, we could also divide up movies into whether or not they were nominated for an Oscar. We might then be interested to know whether a genre of a film is related to whether or not it will be nominated for an Oscar. Somewhat surprisingly, we can accommodate this in the exact same framework. How? Well, note that by adding in this second factor, whether or not the movie was nominated for an Oscar, we are in effect doubling the number of categories. We'll have comedies with no Oscar nominations and comedies with Oscar nominations, action movies with no Oscar nominations and action movies with Oscar nominations, and so on. This means that even though they are being defined by two different factors, we can still separate them all into distinct categories. Then, by doing this, if we want to assume that genre makes no difference to whether or not a movie is nominated for an Oscar, then we can express this in terms of base probabilities. Namely, it would mean that comedy being nominated for an Oscar should have a probability that is given by the probability that the movie is a comedy, times by the probability that the movie is nominated for an Oscar. This provides us with a null model much in the same way as the previous examples. Once we have a null model, we can write out our expected and observed counts for each category. Then, just like in the discussion of other hypotheses tests, we want to construct a test statistic, use this statistic to compute a p-value, and use this p-value to draw conclusions. In this case, it turns out that using the likelihood ratio test statistic derived from a multinomial model suffices. The specific derivation is included in the course notes, so I will provide the final result here. In particular, we take lambda to be given by 2 times the sum of yi times by the log of yi divided by ei. That is, we take the observed and multiply that by the log of the observed over the expected. Sometimes you will see these yi's written as oi's where the o represents observed. Remember, observed times observed over expected. Now, Our expected values here are derived from our expected null model, and when these are correct, we can see that this statistic will make sense. Namely, if our observed value equal our expected value for all observations, then this would be precisely 0. Since this is a likelihood ratio test statistic, we know that the resulting statistic is approximately chi-square. Here we have to be a little careful though, as it's not in general going to be a chi-square 1 distribution. The number of degrees of freedom will generally be given by k minus 1 minus p, where k represents the number of categories considered and p represents the number of parameters that need to be estimated if we assume that the null hypothesis is true. In fact, the k minus 1 represents the number of parameters that need to estimate for the MLE of the proposed situation without assuming the null hypothesis is true. For most of the situations, that will be k minus 1, but there will be exceptions. The degrees of freedom can sometimes be tricky to work out, but there are a number of ways of conceptualizing them, and so I would try to pick what works for you. A lot of people find it easiest to think about it the way that it's been presented here. Count up the number of parameters needed for the unconstrained MLE and the number of parameters in the null model, and then take the difference. This can also be expressed as counting up the number of values that are needed to be estimated before the remaining items can be filled in the table via subtraction. This can also be expressed by counting up the number of constraints that the null model imposes if they are expressed in terms of your standard parameters. My best advice would be to give yourself some practice writing down the model for the approximate distribution and figure out the way that is most natural for you to think about. Once the degrees of freedom have been determined, this approximation can then be used to compute our p-values and draw our conclusions. This essentially defines the entire process that we will follow. We define our problem to be based on categorical data, we specify the null model that we are interested in testing. Using this null model, we compute the expected number of observations in each cell. Then we compute the LRT discrepancy statistic given by twice the sum of y times the log of y over e. We can use this chi-square distribution to approximate the distribution of this test statistic, and from there draw our conclusions. Now, if you've been paying very close attention, you may have noticed that, as stated, we actually cannot go forward with this procedure, at least not generally. The problem is in the compute the expected value step. Think about our example with the fast food chain. If we define theta 1 to be the probability that a given order is a small, theta 2 to be the probability that a given order is a medium, and theta 3 to be the probability that a given order is a large, then how could we codify the null model in symbols? If we take alpha to be the probability that a given order is a small, our null model states that mediums are twice as popular as smalls, or put differently, if the null hypothesis is correct, then theta 1 equals alpha and theta 2 equals 2 times alpha. We could also write that theta 3 equals 1 minus 3 times alpha, but this is implied since we're dealing with a multinomial model. This is all well and good, but if I were to tell you that they wanted to prepare for the next 1,000 orders, how many of them are expected to be small? What about medium? The answer is we do not know. We do know that it would be alpha times 1,000, or 2 times alpha times 1,000 respectively, but we do not know alpha. How can we handle this? Well, we're going to use a trick that has been being applied in several places throughout this course. In particular, this situation is analogous to when we need the standard deviation to apply the central limit theorem, but we do not know it. We estimate it using an MLE. The same is true here. We can compute the maximum likelihood assuming that our null model is correct, and using this MLE, compute the predicted expected values. We use these predictions to compute the statistic and move on as outlined. This gives us the full process. The course notes outlined 3 separate ways of using this technique, and we should go through each of those now. The first is to assess the goodness of fit. If we suspect that data are coming from some model, any model at all, we can ask, how appropriate does that model seem to be for our data? This is a question of goodness of fit. The way that it works is fairly straightforward, given our above discussion. First, we take our observations and make sure that they can be expressed categorically. If this is a continuous distribution, this involves slicing our data into different intervals. If this is a discrete distribution, this may involve binning our responses still. For instance, we may set our final category to be larger than or equal to some threshold for a distribution which can theoretically go up to infinity. Once our data are expressed in categories, next we compute the MLE of our null model. Typically this involves fitting a maximum likelihood estimator in the standard way and then using the invariance property of MLEs to compute the probabilities under the null. These probabilities can then be used to give us the predictions of our expected values. For instance, if our data are assumed to be coming from an exponential distribution, which we have binned into intervals, we would first compute the MLE of the exponential using our data. We know that the MLE for the parameter is given simply by the mean. Then we could compute the probability of an observation falling into any particular interval. This gives us our expected values. With our observed and expected values written in each category, we take our discrepancy statistic and, using the appropriate chi-square distribution, compute the p-value. What is the specific null hypothesis here? Informally, you can think about the null hypothesis as being the null model is appropriate. It will often be the case that this is most easily written down in terms of the multinomial model parameters, but that's not going to happen all of the time. Practicing on various different problems of this form will help to solidify the understanding very quickly. The second type of problem discussed in this chapter relates to cross-classification of a random sample of individuals. In these problems, we have two factors, say A and B, and we want to know whether these two factors appear independent. This is exactly what we were laying out with the movie example. Let's discuss briefly why this problem is exactly the same type. For problems of this variety, we begin in much the same way, with two discretized factors. Now note that if we think about the combined factor of A, B, then we can view this all as a single categorical variable with A times B levels, assuming that there are A levels of factor A and B levels of factor B. The question of interest is whether these are independent of one another, and so we translate this to a null model. If we denote the probability of falling into each level of A with alphas, and the probability of falling into each level of B with betas, then the probability of falling into each of the combined levels using thetas, then our null model will be that theta ij is equal to the product of alpha I with beta j. If these factors are independent, this will be true. Now, in this type of problem, we fix the total number of observations we are considering, and then use these null probabilities and our set total to compute our expectations. Once we have them computed, we proceed exactly as before, with the same likelihood ratio test. How many degrees of freedom will our model have this time? Well, remember, it is given by k minus 1 minus p, where k is the total number of categories, and p is the number of parameters we need in our null model. Here we have already seen k is given by a times b, which is the total number of categories we defined. If our null model is accurate, then we need a minus 1 plus b minus 1 parameters to fit the model, since the joint probabilities are completely defined by the marginals. As a result, this works out to be a model with degrees of freedom given by a times b minus a minus b plus 1. In simpler notation, this is a minus 1 times b minus 1. Now, the final way that this strategy is used is quite similar. In the notes, this final technique is referred to as testing of equality of multinomial parameters for two or more groups. The setup is quite similar to the previous situation. We have two factors, a and b, which we can divide all observations neatly into. However, here we are assuming that group membership in A is going to be fixed. Specifically, for each of the different levels of A, we assume that there is a fixed number that will be observed in each of those groups. The question of interest is then, are the probabilities for each level of B the same, no matter which level of A you were assigned to? One way of imagining this is to set up a multinomial model for each level of A, parameterized using theta sub I over a total of ni observations. Remember, we are fixing the number of observations in each level, in this case to be ni. Then we want to know whether each of these probability vectors given by theta are equal. Let's use a concrete example to help with the understanding. With the COVID-19 vaccine rollout, there are a number of different vaccines available, say Pfizer, Moderna, Johnson & Johnson, and AstraZeneca. Now you can imagine every individual as falling into one of a number of COVID levels, say no COVID, mild COVID, or severe COVID. Our question of interest is, are the vaccines equally effective at addressing COVID-19? Now, because of manufacturing concerns, there are a fixed number of doses of each of the vaccines available at this point, and in particular, a fixed number of people who have received each type. In this case, then, we would consider vaccine type to be the factor A. For each of these vaccine types, we would pose a multinomial model that specifies the probability that an individual does not develop COVID, develops mild COVID, or develops severe COVID. We represent these probability vectors with theta 1 for the Pfizer vaccine, theta 2 for the Moderna vaccine, theta 3 for the Johnson & Johnson vaccine, and theta 4 for the AstraZeneca vaccine. Remember, each of these thetas consists of 3 different probabilities. Then our null model is that theta 1 equals theta 2 equals theta 3 equals theta 4. We can compute the expectations of each where we assume that the probabilities are equal, and then contrast this to the observed value. Now, this is our first model where k-1 does not represent the number of parameters needed under our unconstrained model. If we think about it, for each of our A categories, we need to estimate b-1 parameters without any constraints. For the null model, we need to estimate only b-1 parameters because we assume that it is constant across all different categories. As a result, taking a times b-1 minus b-1, we get a-1 times b-1, which is exactly the same result in the previous question. What this means is that mathematically, whether we assume that the counts in each category are fixed or not, we wind up following the exact same test statistic, following the exact same distribution. This simplifies matters greatly in terms of computation, but it's important to understand the hypotheses we are testing are different and that the situations have arisen separately. Still, it's pretty cool, in a nerdy stats kind of way, that the same test can be used in all of these different scenarios. What's more is that this is a test that is actually used all of the time. If you were taking stats just for the real-world applications, understanding chi-square tests alongside Gaussian response models are probably the two most important techniques for application.